All right, well, hi everyone. Thank you for joining me tonight. My name is Yanina Barrera. It's actually spelled with a Y. It's Argentinian pronunciation, and I'm a PhD student studying environmental science and engineering. And today the title of my talk is Air Pollution Knows No Boundaries. And I'd like to talk to you about some of the work that some of the atmospheric scientists are doing to try to understand air pollution in cities. In this talk, I want to point out that I'll primarily focus on carbon dioxide emissions because it's a primary greenhouse gas emitted by human activity, but I will not discuss the climate change implications on this. So first, I'm going to turn it over to the audience. What air pollutants do you think are of major concern when it comes to, let's say, combusting coal? Right, great. Anybody else? Think of other pollutants with the combustion of coal? Okay, so gentleman was right. Aside from carbon dioxide emissions, we also have sulfur dioxide emissions, but we have particulate matter, which is suspended particles in the air. And the composition of the particles can sometimes contain toxic metals, such as mercury compounds, right? So mercury is actually of huge concern when it comes to the coal power industry. We also have sulfur dioxide emissions, that was correct. And we also have nitrogen dioxide emissions. And so what's great about studying carbon dioxide emission in cities is that we can also look at its co-pollutants. We can look at the other pollution that is going along with this. So before I begin though, I want to ask the question, how did we end up here with air quality regulations? What were the events that led up to having air quality regulations? So first, there's a well-known event. It's called the Donora Smog Event of 1948. Donora is a city that is located south of Pittsburgh. It's heavily based off of coal production. And at the time, the population was about 14,000 residents. And in late October, there was 4 days of heavy emissions of silt and sulfur dioxide emissions from steel mills and zinc smelters, so essentially steel making, metal making industry, and it resulted in the deaths of 20 people. Half of the Donora residents also developed respiratory illnesses. And so events like this, smog events like this, resulted in the need for regulation of air pollution, which led to the 1955 U.S. Air Pollution Control Act. And similar to the Donora smog event, 4 years later, we have the 1952 London Great Smog Disaster. And it was a 5-day severe air pollution event that killed over 4,000 people. And it's actually the largest known air pollution disaster in the UK. So essentially what happened was you had this period of cold weather and stagnant air that essentially trapped the air pollutants from coal combustion, which was heavily used in London, near the surface. And even though this is a significant event, 4,000 people were killed, it was actually pretty frequently experienced in London. And so this really prompted the need for having regulations. And just 4 years later, you have the UK's Clean Air Act of 1956. But it wasn't until the US Clean Air Act amendments of 1967 that we actually have the control of hazardous air pollutants in the US. Thereafter, we have the US Clean Air Act amendments of 1970, and that's when we have the establishment of the Environmental Protection Agency, so the air quality authority for the US. And then in 1990, we have the next Clean Air Act amendments, which did more controlling of not just stationary sources, but as well as mobile sources. And most recently, we have the Paris Climate Agreement. So the Paris Climate Agreement happened back in December of last year. And we, as the United States, have agreed, we volunteered and agreed that we should do something to mitigate carbon dioxide emissions in the United States. And as some of you may already know, carbon dioxide concentrations in the atmosphere are the highest that it's ever been in 800,000 years of ice core data. So concentrations of CO2 have nearly doubled. And the Paris Climate Agreement really pressed for the need to really be able to monitor, report, and verify carbon dioxide emissions every 5 years and find ways to mitigate these air pollution sources. So in our research group, we're doing our best to develop a prototype in order to regionally monitor carbon dioxide emissions, with the ultimate goal of providing stakeholders with the tools necessary to formulate and monitor effective greenhouse gas mitigation plans. But this problem is actually global, right? And so that's why it requires nations to come together and to agree that they want to do something about carbon dioxide emissions. So what we have here is a visualization video of 2006 carbon dioxide levels compressed in just a few minutes. So you'll see on the left-hand corner here, date as time passes by, and you also see carbon dioxide concentrations shown in red, enhancements of carbon dioxide concentrations shown in red. And so when I play this video, what I want you to notice is that carbon dioxide doesn't stay in one place. One second. So as you can see, time passing by, you can see that carbon dioxide emissions are transported globally in our atmosphere. And what's important to note is that half of the carbon dioxide emissions from human activity remain in the atmosphere, while the rest of it is removed by land and ocean processes. Over 1/4 of the world's carbon emissions are actually attributed to North America, and that includes Mexico and Canada. And in the case of CO2, much of today's emissions will be gone in a century, but 1/5 of it will actually remain in the atmosphere, and it'll exist in the atmosphere 800 years from now. So as you can see, what we are doing today with human activity impacts the atmosphere years and years from now. There are several greenhouse gases, but carbon dioxide is the most popularly talked about because it remains in the atmosphere for longer periods of time. For example, water vapor is a well-known greenhouse gas, but we don't talk about it very often because it's removed through the atmosphere through the Earth's cycle very quickly, for example, through precipitation. And as you can see, concentrations of carbon dioxide remain pretty high over the northern hemisphere. And as the summer months start to unfold, then we start seeing a seasonality change. We start seeing less CO2 emissions in the atmosphere because we actually have vegetation growing. We have the growing season, and some of that is actually removing carbon dioxide from the atmosphere as well. So that's important to note because the carbon cycle has many complex processes, and in order to understand CO2 emissions in a city or regionally in a state, we need to understand kind of the terrestrial biosphere and what is occurring. So we have carbon emissions from industrial, commercial, and transportation emissions, human activity. And we also have carbon that's introduced into the atmosphere from forest fires. So if I were to replay that video, you would see in the summer months, we would also see an enhancement in carbon monoxide, for example, because of forest fires. We also have CO2 emissions from respiration, and we also have carbon dioxide that's removed from photosynthesis. As you know, plants make their food from sunlight and carbon dioxide. And we also have these longer term processes that take about millions of years to essentially store the carbon into sediments and into rocks. And we also have the uptake of carbon from in the ocean as well. But for our case, when we're trying to study carbon dioxide in cities, we're actually more interested in the biosphere, the terrestrial biosphere here, which means we want to look at the emissions that humans are bringing into the atmosphere, but also look at some of the removal processes that are happening currently right now on smaller timescales. So tonight, I will discuss how we use models to understand air pollution in cities, what cutting-edge technology scientists are using both on ground and in space to understand CO2 emissions, and in the end, what do these instruments and models tell us? So first, how do we use models to understand air pollution in cities? First, a model, we want to clear up, is not the real world, but it's a human construct to help us understand real world systems. So a model can mean both the computer program itself and the concept. And models are accepted in the atmospheric science world if the results are, if we find supporting evidence for the results and the results can be repeated again. And we can actually use models with observations to give us a better understanding of what we are trying to learn in order to evaluate uncertainties. So a common model that you use every single day, potentially, could be Google Maps, right? You have it on your phones. And it's a model. It's trying to represent how long it would take, for example, for you to get from point A to point B. And there's different inputs into this model, into Google Maps. It needs to know traffic data. It may need to know changes of road elevation, for example, to see how long it's going to take for you to get there. But when you get in your car and you're driving, you're trying to figure out what the roads look like in comparison to the model. Is the right turn I'm supposed to make right now, or is it right after the overpass, for example? And then you may get on the freeway, but suddenly there's a car accident right in front of you, and it slows you down to get to your next destination. So models are trying to do their best job to understand what's going to happen in reality, but again, it's not the whole picture. And so what we do as atmospheric scientists is construct many models in order to understand the systems in the carbon cycle that I just highlighted. So how do we build models in order to better understand air pollution in cities, especially when the air is constantly moving around us? Well, first, in order to get an optimized estimate of carbon dioxide levels, both spatially and temporally, because it does have seasonal changes, we want to include information about emission sources, but we also want to include information about the transport, which means we want to add information about the wind and weather. And we also want to include information about the biosphere itself to understand some of the removal that may happen during a certain period of time. And then we can also take measurements from instrumentation observations to try and better understand the uncertainties in the models or test the models themselves. So we don't always want to believe the model. We always want to continuously test it to see if it's a good representative model. Here's an example of a model product from a transport model. And essentially this model product here is we want to know where the air pollution came from, so we can actually track it backwards in time. So this is a footprint or a map here, and it's showing the sensitivity that the particles that see the surface observations. So essentially we want to know why we're seeing enhancements of carbon dioxide levels in the city of Boston. And we can go backwards in time in a transport model, including information for the winds, in order to see where the source regions are showing sensitivity to what perhaps we're seeing in Boston. So this date is actually November of 2012, going 16 hours backwards in time. Can you think of potential sources in the New Hampshire, Vermont, northern Massachusetts area that may be contributing to perhaps the observations in Boston? Can you think of an emission source?
Route 93.
In fall, that's right. Okay, we could have traffic sources. Route 93 is a big one, that's right. Can you think of something else related to maybe colder temperatures in the fall? Well,
Wood stove.
yes, exactly. So wood burning. Wood burning is actually very popular as space heating. So we could potentially, for example, ask the question, you know, are the particles perhaps sensitive to wood burning in the winter time? And so we can ask these sort of questions by kind of tracking these particles back in time on a map. So these transport models essentially work by you set the location of where you want to understand your concentrations of CO2, and you're going to release imaginary particles backwards in time in this model, okay? So you can release 500 particles, 1,000 particles. The more particles you release, the more computationally expensive it can get. So you can release it backwards in time and try and track these particles on a map, just like the model product showed you, in order to get a better sense of potentially the emission sources that contributed to the enhancements of CO2 in the city of Boston, for example. And we can actually do this 3D. We can track it horizontally, spatially on a map, but we can also track it vertically into the atmosphere. So we can look over time at different heights in the atmosphere to potentially see which local sources, for example, were contributing to the enhancements in the city of Boston versus which ones were non-local.
What are you tracking it with?
So we're tracking it with the model. So essentially we have a model that has plenty of math and physics.
You must have some kind of a measuring instrument that you're using.
The particles themselves.
Yeah.
So we essentially, we model with physics and information from the weather and wind, how those particles would have, where those particles came from. So we can actually track over time where those particles were most sensitive to on a map. So it's essentially a model telling us.
That part I understood, but I'm sorry.
No, it's okay, okay.
Back to the first slide you showed with the red and stuff. Where did that information come from? Did you have like something from a satellite that saw it, or?
Yeah, so essentially the model product itself, it gives us an output of information. So for example, it will tell us how many particles are located during in certain section and grid cells of the map based off what the model thought the particles were doing backwards in time. And so then I can collect all that data and spit out a map. I can calculate, I can transpose this information and put it on a map to essentially get a sense of where the model sees the particles. So it gives us this image. So we do this with a computer program with lots of coding. Yes. Okay, hope that answers your question.
Also, as just a reminder, we have a designated time for questions. So.
Oh, okay, great. That's good to know. And we can talk about this more offline as well. So, but okay, so we have a sense of where these particles are backwards in time. So essentially, which ones are showing sensitivity to the enhancements in the city of Boston, for example. But it's an empty map, essentially, because we need to know what the emission sources are along that map. So we integrate information about the emission sources itself. And what you're seeing here is a product of Connor Gately at Boston University. It's a 1 kilometer high resolution map showing the on-road carbon dioxide emissions inventory. So essentially here, is that the 93? There we go. 93 right there. So here you can see we can understand spatially using traffic data and measurements where we think the emission sources are in this map. So if we combine information from this map along with the information of the particles that we track backwards in time, then if we see there's a spot where it seems that the observations in Boston are really sensitive to the source region, then we can perhaps identify those sources or try and quantify them. And perhaps then give recommendations into mitigation. Let's kind of reduce the air pollution in this source region, for example. So in summary, transport models are heavy computationally and expensive to run, but they help us study air pollution locally and regionally by being able to track the particles backwards in time. And information about the winds can help give us more details as far as where we think these emission sources came from. And the emission inventory itself, understanding the sources that are located in a state or in a city or regionally, can help us identify those emission sources themselves. Okay. So break for questions. Does anybody have any questions on the first part? Yes.
Is it expensive because of all the wind and transport data that you would need, or is it expensive because of the computer that would need to run the simulation on the model?
It's not it's not necessarily because of the computer. It's just it takes a lot of hours. It's it's a very sophisticated model. I mean, we're including a randomness component to it, a stochastic component to really kind of convey the real world transport of the air, how air parcels individually are moving throughout time. So there's a lot of physics, there's a lot of math, and there's a lot of inputs into those models, and all of those need to be validated and checked. And then also you're releasing particles, many particles backwards in time and tracking them at every hour. So it's very time consuming. So this can take up to a few months if you're being really fast and in order to try and understand where the particles came from. So it's not something necessarily that the Environmental Protection Agency would do, but it's something that we can use our results and our models to test their models to see how they're doing, or perhaps try and make it more inexpensive. But it's not necessarily the computer itself, it's time consuming, and there's a lot of details that go into it. Yeah. Without going into the complicated details. Any other questions? Okay, great. So the second part, what cutting edge technology do atmospheric scientists use both on ground and in air and in space, for example, to try and understand what carbon dioxide levels actually are in the atmosphere? So we talked about models, a representation. So before we begin, and something that is very important is the lowest layer of the troposphere that expands from the ground to the bottom of cumulus clouds. So sometimes if you're in an airplane in the airport and you can see the flat tops of the clouds where it gets flat underneath, that's essentially the layer that's called the planetary boundary layer. And this layer is actually very important to model correctly in the transport models. A main reason is that its behavior is influenced by surface forcing. So what we're doing based off human activity here, from incoming solar heat, and also from vegetation and topography. And this planetary boundary layer is essentially what contains the air that we breathe in. It traps the air that we breathe in every day. And so knowing where the height is and essentially the concentration of air pollution will be dependent on that height. And so we need to model this planetary boundary layer correctly, and the problem is it's not a constant layer. It's constantly moving, right? We have surface winds, we also have cloudy days, and we have surface cooling, but we also have sunlight coming in and heating up the surface. So it's constantly warming up and cooling down. And in the daytime, what we have is incoming solar heating that heats up the Earth's surface and essentially starts to mix up the air because it's getting warmer and warmer. And we also have the heat island effect as well. We have more concrete, we have more buildings that can also add additional heat into the system. And essentially we have the formation in the early morning to late afternoon of this planetary boundary layer. And so modeling this is extremely important, especially in cities, because we have the urban dome effect, which essentially over cities, this planetary boundary layer can actually get higher because of the heat island effect. So in the city of Boston, the planetary boundary layer can be up to 1 kilometer or even 2 kilometers throughout the day. And so being able to correctly model this will help us really understand the air pollution that we're seeing in cities. And this is the same planetary boundary layer that was of major concern. For example, in the Donora smog event and in London, in the winter time, the layer is lower and it traps those gases closer to the surface. It means you have higher concentration and you have adverse health effects. And that's what you see in China as well with some of the issues in their haze in the winter time. And of course, we care about this layer because the higher the layer it is, the more diluted the concentration of air pollutants will be, and the lower the layer is, the higher the concentrations can be. And so that has public health implications as well at times, and it's important for us to model that correctly. So we try to model that layer with transport models that I showed you before, but we actually want to have a way to measure it so that we can test those models to see if they're actually doing a good job. And a way we can do that is using LiDAR technology. So LiDAR stands for light detection and ranging, and it's a surveying technology that has been used to make high resolution maps in the past. And it can also be used in atmospheric science to measure the distance of clouds or objects. And objects can even be haze in the atmosphere. And you can target that with a laser light. So let us explain how this LiDAR detects, how this LiDAR works. So what we have here is that LiDAR sends out a pulse of light, and also then detects the return of light. So what happens is that when you have a cloud, let's say for example, it will detect the backscattering. So you emit a pulse of light, and when the light returns, it's essentially detecting the backscatter, the deflection of the light particles at an angle of 180 degrees. And so that's what LiDAR technology is doing in the atmosphere. It's detecting the backscattering in order to see structures or measure where the objects are in height vertically. And we can measure the intensity of that backscatter at each height point continuously, 24 hours a day. Now remember though that in one LiDAR pulse there are actually many returns. So again, let's say we have a haze layer, okay, some smog event or haze in the air planetary boundary layer, and let's say then it's topped by a cloud. Well, when we are emitting this pulse of light, it's going to backscatter from both the haze layer and it's also going to backscatter from the cloud. And so we're going to see larger signals in the atmosphere. There's going to be air pollutants or dust or particles in the atmosphere throughout the whole thing, but there may be some layers, larger layers that give us a larger signal of possibly detecting a cloud or haze. So now how does the LiDAR actually store the information? So we have a pulse of light and then the return of light, and we detect it. Oh wait, I'm sorry. So how does LiDAR actually calculate the height of where this cloud is? So we emit the pulse of light and we detect the return of light. And we can understand the distance because we know how long it took for the light pulse and return, how long it took to get there, to get back to the detector, as well as we know the speed of light. And with the speed of light, we can then have a sense of distance. But because it's backscatter, it means it takes two pathways. It goes up and down, so we just divide that by 2, and we get a sense of the height of where this cloud is. Now, LiDAR stores the amount of light returned as photons. And if you remember from physical science in high school or in your class, it also exists as discrete particles called photons. So LiDAR is detecting the amount of photon counts that come back every single time. So what we have here in blue are time bins, okay? The LiDAR system itself measures photon counts every 200 nanoseconds. So it measures it continuously all the time. And so what we have here is photons that it counts in every time bin. So can someone tell me here, how many photons does the first bin see? 3, right, perfect, thank you. Okay, how about the second one? Okay, you can yell it out with confidence. The third?
3.
Okay, great. And so on and so forth, right? 3, and we have finally 1. And so essentially it does this every 200 nanoseconds with many photon counts. And the computer program will store this information, and then we can download in a software, and then we can download the data and further analyze it. So this is what we get. I made it simple, and this is the image that we can actually get. So what we have here, what you're looking at is height of the atmosphere from 0 to 5 kilometers, okay? And you're also looking at 24 hours in a day. This is on August 21st of 2013. The more backscattering that the LiDAR sees, the higher intensity it is. It's mapped in red and white colors. And the less backscattering, fewer particles it sees, it's in the green to blue colors. So in the morning hours, during sunrise, remember we have the growth of this planetary boundary layer that is important for us to understand where it is. And so we can actually see here the curvature of this planetary boundary layer forming, because in the morning hours, we're going to see this growth of this planetary boundary layer, but there's also a new source of particles in the atmosphere. In the morning hours in the city of Boston, can you think of emission sources?
Traffic.
Traffic, exactly. So we have traffic, cars, particulate matter from cars, aerosols that are emitted into the atmosphere in the morning, and we can see those particles being mixed into the atmosphere. So LiDAR is actually able, at times, not always, to image this planetary boundary layer growth. And part of my research here was to create an algorithm using image detection and signal processing to be able to pick out that curvature itself. And so, as you can see, at times it's pretty successful, and we can capture the growth of this planetary boundary layer, and then we can compare it to different different transport models that use physics, for example, and math to try and understand what the height of that planetary boundary layer is. So great, we can use LiDAR technology to measure the height of the planetary boundary layer. But now let's talk about carbon dioxide again. Now we want to understand what the carbon dioxide emissions are in the atmosphere itself. So as part of NASA's carbon monitoring system and Harvard University, we have a Northeast measurement network, okay? And so here in the city of Boston, we have 2 sites where we take measurements of CO2 levels. One in Copley Square, that's located in one of our tall structures. That's 215 meters above ground, and also in Boston University, that's 30 meters above ground. And we also have another site in Harvard Forest. And what's great about this site is that it actually takes measurement at 8 different levels of CO2 because we also, in the forest canopy, as we said before, through photosynthesis and respiration, we have the removal of CO2 in the atmosphere in the forest, and we also have the emissions of CO2. So we constantly are looking at the emission flux. So what the Northeast network is telling us here is that we also, why this is important is to have these multiple sites. We want to know the enhancement of carbon dioxide levels in the atmosphere. That means we have to have a sense of what the background CO2 levels are, right? What the background already has and how much is being enhanced by a city, for example. And so Harvard Forest itself is showing here in green that the carbon dioxide emissions concentrations are cleaner, let's say, than the Boston sites in Copley and in BU. And this is important because we want to be able to subtract the background air from the concentration we measure in the city so we can actually see what the true enhancement is. And actually, one thing I'd also like to make a note of is Copley is at, our measurement site at Copley is 200 meters above ground, and our measurement site at Boston University is 30 meters above ground. So as you can see here, Boston University has higher CO2 levels because it's located closer to the surface, right? So it's seeing more of those emissions. It's seen at higher concentrations because it's not being mixed up as in the atmosphere as high quite yet. We can also measure CO2 levels from space. And what we have here is the Orbiting Carbon Observatory 2, also known as OCO2. It's a NASA satellite. It was launched in July of 2014 and starting taking measurements in September 2014. And so essentially the NASA satellite wants to track carbon dioxide emissions around the globe, just like that simulation was trying to do, track it every single year, and essentially the satellite orbits the planet to take these CO2 observations and return to those sites. So it orbits the planet and returns to those sites every 16 days. And you may be wondering, it's in space, it's a satellite, how well is it actually measuring carbon dioxide levels on Earth? Well, OCO2 can measure carbon dioxide levels with a precision of about 1 ppm, 1 part per million. And what does that mean? Well, today's carbon concentration is about 400 parts per million, okay? So that means that you have, in 1 million molecules of air, you have 400 molecules of CO2. And the satellite can measure with a precision of 1 ppm. But, okay, who cares? It could do 1 ppm. What does that actually mean? Well, atmospheric scientists actually monitor the background levels of CO2, just like we're doing, for example, in Massachusetts with our Northeast measurement network. They're also monitoring the CO2 levels Mauna Loa, Hawaii Observatory, okay? And so the recent monthly average of these CO2 levels shows that we are at about 404 ppm, okay? And last year it was at about 400 ppm. We're already seeing a 4 ppm difference in 1 year. So it means that the satellite has a precision to at least monitor these differences between year to year to see how CO2 is changing over time around the globe and the seasonal and spatial changes. Okay, so does anybody have questions? Yes.
Relative to that 400, what were those levels in the Copley, Harvard, and BU rack?
Yeah, that's a great question, and I'll actually be talking about that in my third part for the results. But the levels are levels that we're seeing can be up to 440, 50 ppm in Boston, the city of Boston itself. So it's an enhancement about 40 ppm of CO2 levels, and I'll show that in the next section as well. Go ahead, question.
The planetary boundary layer,
Yes.
is that determined strictly by temperature, or are there other factors?
The planetary boundary layer is very complicated in the sense that it does not have a single definition. Okay, so it experiences temperature swings compared to the rest of the atmosphere. So it could be defined by its potential temperature, its relative humidity, and there's different physics and factors that kind of go into determining that. So you can measure the planetary boundary layer with also radiosonde data. That's also something that's used. Weather balloons that are essentially like going up and down into the atmosphere and taking measurements of relative humidity and pressure to determine kind of some of those factors that also defined the PBL. So there's actually quite a lot of definitions of the planetary boundary layer.
The air above the planetary boundary layer, that air doesn't really mix?
So actually, yes, that's a good question. The air, what I'm seeing with my LiDAR is that we actually do have what we call a residual layer. This layer that remains overnight and sometimes over the daytime in the city of Boston. And what that means is that air pollution from the previous day can remain in the atmosphere at night when it's cool. It's just stratified in the atmosphere. And then when you have the solar heating, sun heating up the Earth's surface, this mixing starts happening, and it can entrain, it can pull down some of those air pollutants from the previous day that were at night, stored at night, for example, into the boundary layer. So it could either be pollution at night, either from the city itself, or it can be pollution from the previous day that remains in the air, because it's quieter, it's a quieter air, it's less dynamic, right? It's not as mixing as much. So one thing that we're actually potentially going to be doing is, one thing that you can look at is tracking the particles as they go in and out of that layer. So you can see whether or not we're seeing higher pollution in the atmosphere, not because of local sources, but because it came from elsewhere. So it's a very complicated science, but people are doing things to kind of understand what's locally influencing the air pollution in that PBL, for example. Yes, another question?
Well, you were talking about the level being lower at Copley than at BU because Copley's higher.
Well, the level of, okay, so the level of the planetary boundary layer isn't lower at Copley. Our site itself is lower.
The level of CO2
Yes.
in the sensor data at the Copley
That's right.
altitude, you said was consistent.
Typically, yeah,
Lower than the level measured at the BU
that's right.
site because it's BU's closer to the ground.
Right, so it's seen, but again, you could have a jet stream of wind
Right.
blowing up,
So
yes.
Assuming for the sake of argument that the air was relatively static, there's not a lot of, there's not a major northeaster taking place. It's bringing all the wind from the side. And assuming that the source of the CO2 is all like on the sidewalk where people are throwing, cigarettes on the sidewalk or whatever.
Okay, sure.
Why are you thinking of the level as automatically being lower when you're higher up?
Why are you thinking?
All the CO2 that's being delivered to the sidewalk has to diffuse outward in
That's
some
right.
uniform way.
Right.
So like if we thought of that CO2, I know this is a silly example, but if we thought of all that CO2 as leaving for the moon, it would be like a train of CO2 headed vertically. We would have to see the same amount of CO2 at each.
Well, it's constantly mixing, so we don't.
I know it's constantly missing,
Right.
but I'm saying the simplification would be the CO2 is delivered to the sidewalk
Right.
and it goes somewhere. Like it goes really high and then ends up in the ocean. In some simple model like that, the amount of CO2 at each railroad car along the way would be the same amount of CO2. Why would it be more concentrated at the 100 feet off the ground than 200 feet off the ground?
It's closer to the source in terms of time.
But it doesn't go away when time passes, it just moves.
But it's still being generated.
Yes, but the CO2 isn't breaking down into something else.
No, the CO2 remains, it's globally
still
mixed.
CO2, right?
That's right. It's still, so there's going to be removal processes, right? So there's that biosphere component. And so we have to keep track of it, the emission fluxes with time in that layer itself as well. So there's removal processes too. So not only can it be more concentrated, but it can also be removed, but not by other processes as well.
Being removed between the top of the U and the height of this Copley Square building.
I guess I'm not really understanding your
The
question.
CO2 isn't being taken away between the top of the U and the top of the Copley building. The CO2 is just diffusing in the atmosphere. Right? It's not actually being turned into something other than CO2. And it's not being taken away by plants right there. So it seems like it's not clear where the, I'm just trying to understand how do you, if I know the real world is extremely complicated, so you can't answer the question except
Yeah, I guess if you would have to model that to be able to understand. If we do create those simple models to eliminate other factors and see what CO2 concentrations would look like. But in this case, it doesn't always see, just because it's lower, it doesn't necessarily always see, I guess you can say, the highest concentrations. But it is constantly being mixed, and because it's getting more of the plumes from the sources on ground, it's going to see higher CO2 concentrations. Okay, so we talked about how atmospheric scientists use models in order to understand air pollution in cities. And next we're going to talk about, and then we talked about the cutting edge technology some of the cutting edge technology that scientists use. And trust me, there's other measurements out there and devices out there, technology to look at CO2 levels. But what I will talk about next is what do some of the instruments that I just talked about tell us about air pollution in cities. So again, what we have here is the Northeast Measurement Network. And just to remind you, we have the Harvard Forest site that is used as our background site. We also have the Copley Square site. We take measurements 250 meters above ground, and we have Boston University at 30 meters. And so from what we saw before, we saw that carbon dioxide levels in Harvard Forest are relatively cleaner than they are compared to our Boston sites and locations. And this is a good thing because we want to know what the background air is so that we can subtract it off from our enhancements or from the emissions seen in Boston, in the city of Boston, so we can actually see what enhancements we're showing. And just to clarify, sometimes we can really see carbon dioxide levels be more concentrated closer to the ground because that's where the emission sources are. And so at times we can see higher emissions at Boston University, but it's not always the case. So let's look at some of the results here. So what we see here is CO2 concentrations as a result from our model and measurement sites at Boston University and Harvard Forest here on the right side. And what you see here on the left is time, 24 hours. And at the bottom you have your months. And you have your winter months located in the center, and you have your summer and spring months located at the edges. And the concentrations here are in ppm, and the heat map in red are about 440 ppm in concentration. And then we have in blue and green about 400 ppm, which is the background level that we discussed before at Mauna Loa Observatory. So here, can someone maybe perhaps highlight some trends that you see here? Where do you see higher concentrations of CO2 levels? Let's say in Boston University.
Noontime.
Okay, so one is, okay, right at 12 UTC, which is actually, it was actually converted to -4 hours, so it's morning time. So morning time, correct. And someone else mentioned something? Winter, right, exactly. And so what we're seeing here is that during the winter months, we have, what do you think is going on in the city of Boston in the winter time? As far as sources go.
Heating.
Heating, exactly. We have space heating. What else is happening in the morning in the city of Boston?
Traffic.
Snow plows. Yeah, traffic, that's right. And we have snow plows, that's right. And so what you can see here is we have an elevated enhancement of concentrations of CO2. And we can compare that to Harvard Forest. And so at Harvard Forest, our background site, you can see here that the concentrations kind of lie around, what is that, 410 to ppm. So we see an enhancement at about 40 ppm, let's say, at Boston University in the winter time during the morning hours. And we can also see some of that happening here and at midnight, because some of us are still heating up our homes, for example. And one thing that we can also notice at Harvard Forest is here. So we also see a reduction in carbon dioxide levels at Harvard Forest, let's say in the summer months and in the spring months. Can someone tell me why? Can you say that louder? That's right. So we have photosynthesis, right? It's our growing seasons. So it's actually our growing seasons, and so we're actually seeing the removal of CO2 happening at Harvard Forest, right, from our vegetation. And we can actually still see some of that drop in CO2 levels even at Boston University. So with a few ppm, the vegetation in the growing season can actually also remove carbon dioxide levels from the city as well. So the results of this pretty much show that the influences of traffic, of space heating, and vegetation are manifested in the daily patterns of CO2 concentration across the seasons here. Okay, so I showed you before how we can actually image with LiDAR the planetary boundary layer height from the morning hours until the early afternoon. And we can also compare how that height, the planetary boundary layer height, is doing in comparison to models, okay? So we have two models here that are using physics and math and wind information to understand where they think that height of that planetary boundary layer is. And you can see that sometimes it doesn't do a great job. For example, model 1, here shown in purple, it kind of thinks it doesn't have as fast of a growth rate as the LiDAR is showing. And we're also seeing here that the second model in green, that the planetary boundary layer is collapsing very quickly, and that it only reaches about 700 meters height, whereas the LiDAR is showing up to a 1.5 kilometer height, peak height of the planetary boundary layer. So what does that mean? What if the model doesn't do a good job of capturing what our measurement are showing us? Well, I'm trying to create in my research a framework for creating quality flags to understand this. So what if the PBL height does not agree with the LiDAR observations, or maybe not just the LiDAR, but other instruments that are trying to understand the height of the planetary boundary layer? And so we are able, with our transport model, for example, to track the particles backwards in time, both horizontally and vertically. So one thing that we could do is we can try to see how many particles, for example, are above or below the boundary layer according to the model. And so a concern with the models not matching up with what instruments are telling us is that the particles may be biased low or high to the land emission sources if we don't model it correctly. So first, let's say we have the LiDAR height. Okay, so we have height here on the y-axis, and let's say we have land emission sources here. Okay, let's just pretend this is a footprint with land emission sources. And that's what our LiDAR height is telling us, okay? At a certain point in time, we have this LiDAR height, our observation. And let's say the model height is too high, okay? Now let's also look at the second scenario where the model height is too low. What that means is that these particles located in this lower layer that the model thought the planetary boundary layer should be are going to be biased high. In other words, there's going to be higher CO2 levels observed. And we're also going to see the opposite, lower CO2 levels than observed, and the particles will be biased low. So we want to be able to create a framework where we pretty much test, how good of a job is the model, or how well is the LiDAR height agreeing with the model. And if it's not doing a good job, then we should remove those days. We shouldn't trust answers from our model as far as trying to understand the CO2 levels in a city if we're not being able to model this layer correctly. So if the LiDAR measurements do not agree with the transport model, we should not use or rely on these dates or model results, or we should go back to our original model and how we set it up and see if we can change the physics or parameters so that we can try and model this height better. And if they do agree well, then great. Then we should be able to trust the study of transport of air pollution in the cities if we're getting this layer correctly. And so what we're doing is trying to develop a framework to identify uncertainties. So let's look at an example of a good date. So what we have here is July 5th. And, oh yeah, okay, I'm sorry. So this is actually July 5th of 2013. And what we have here is, again, we have a clear signal of the planetary boundary layer growth in the morning to the early afternoon as expected in the daytime. And our model product, our transport model, is showing that if we look 4 hours backwards in time, the observation, or our location starting at the city of Boston, the particles are showing sensitivity along the coastline, okay? So we can see, based on the location that we've chosen, the city of Boston, 4 hours backwards in time, the particles released backwards in time, what locations or source regions are contributing to the observations themselves. And so what we see here is along the coastline. So can some of you guess,
Fireworks.
There you go. Can you say that louder?
Fireworks.
Exactly. So it's July 5th, right? It's post-Independence Day celebrations. So July 4th fireworks. So that's exciting. So because we were able to get this model product, transport model product, this is just one of many cases, of course. But because we know the particles are influenced by sources along the coast during the July 4th, then we can potentially say, okay, well, if July 4th is in fact, a big source of combustion in the atmosphere, then we should also be able to track some of its co-pollutants. So when fireworks explode, what do you see right afterwards? You see smoke, right? And so we see particles in the atmosphere. That's particulate matter. And so what's interesting is that with fireworks, the metals that are most commonly used in fireworks, for the color blue fireworks, they're composed of copper chloride. For the red fireworks, they're composed of strontium carbonate. And for the orange fireworks, they're composed of calcium chloride. So I was able to flag, okay, maybe July 4th is showing us a source of air pollution in the city of Boston based off the wind information. And we also have data located at the Harvard School of Public Health. they actually take particles because they're concerned about the public health effects, and they try to measure the composition of those particles themselves. So we can actually speciate the particulate matter, the suspended particles in the atmosphere. And they actually do take measurements of the metals copper, strontium, and calcium. So if that's the case, then I should see enhancements of these metals in the atmosphere as well in the city of Boston around the July 4th celebrations. And so what you can see here is that we do see enhancements of calcium, we do see enhancements of copper and blue, and we also see enhancements of strontium and red. And that confirms that this is truly, it's another way to build evidence to show that fireworks in fact were contributing to some of the enhancements that we saw in the city of Boston. So we can do this, I mean, we can look at local pollution and try to also look at the pollution that is coming from elsewhere. So we can really see, where the mitigation needs to happen. Perhaps maybe Boston is being polluted very often by some of these other locations. And some of my other work also looks at looking at other states and regions that are polluting the city of Boston. So, great, CO2, carbon dioxide levels, they can also tell us about some of the other pollutants that are emitted along with it. But what we really care about is how much CO2 emissions will the carbon cycle continue to absorb in the presence of climate change, right? That's what we want to Paris for. So in the climate agreement, we want to be able to track and monitor carbon dioxide globally. And so in order to do that, we really are trying to develop these integrated data model networks, okay, a framework, to essentially be able to test the model with measurements and then improve the model so we can do a better job of depicting the real world of what we actually are seeing in the atmosphere. And so all of this work is to essentially be able to understand what the CO2 levels are in the city. So yes, it's a global problem, but the action is actually happening at the city level, right? So 70% of carbon dioxide emissions from human activity are actually happening at the city. So we want to do a good job of monitoring, of verifying, and reporting the CO2 levels. And because it's a complicated system, we need these models and instruments to be able to do that. So in conclusion, atmospheric scientists use various high-precision instrumentation networks in order to be able to understand the levels of air pollution that we're seeing in cities or in regions. And the carbon cycle is complicated, and the biosphere itself has many inputs and outputs. And so we want to be able to look at the whole picture. And so in order to do that, we use the power of computer programs to create these models, to incorporate these more complex processes so you can have a better understanding of how it all works together when the surface emissions and human activity are constantly changing, right? Every single day. Even the landscapes themselves are changing. We have new cities that are growing, for example. And of course, air pollution knows no boundaries. Oops, sorry. So we need to understand the transport, and these transport models that incorporate physics and math are key for us to understand where the air pollution previously came from so that we can subtract what's local and non-local. And of course, with the Paris Climate Agreements, it calls for us to really understand the areas and cities and states and countries where it can improve its infrastructure or mitigation strategies to reduce CO2 levels. And with that, that's it. So thank you. So I'll take any last questions. Yes.
Is there,
Sorry.
using the Harvard Forest as the baseline,
Yes.
wouldn't it be better to use a smaller city because the forest, just because of the photosynthesis, is actually reducing it? So wouldn't the number not be neutral, but like lower than it should be because it's actually removing CO2 from the atmosphere?
Well, yeah. So what we try to do is understand the enhancement in the city itself. So we don't want to compare it to another city because not every city is created equally. Okay, so for example, one study has showed that New York City its carbon dioxide footprint per person has actually decreased over the year because people are actually are choosing to take public transportation more. The same case is actually even for Los Angeles and even in the city of Boston. And so each city has its own, fingerprint, right? So they all have their own emissions activities. They have different industry type sources. Some may be more metal making, whereas others maybe only have traffic. And in the city of Boston, most of the emissions that we're seeing will either come from heating, from commercial buildings, or from traffic sources itself. So to find another city like that to compare it to is a little tricky. And we can't compare city to city, but what we really want to do is subtract the background air, what's around it. And so we actually don't just have Harvard Forest sites, we also have Martha's Vineyard, we have Thompson Island, and we also have the Cannon, New Hampshire site. So we actually have several background sites, and depending, I didn't state this in my talk, but depending on the direction of the wind, we can utilize one site as the background site in order for us to really see the enhancements. We do compare cities to one another, but to really see the enhancement for Massachusetts, it's fair to compare it to Harvard Forest, Martha's Vineyard, and so forth, to kind of see what kind of enhancements we're seeing with the anthropogenic component of it. Yeah.
So what's the current state of computer modeling for atmospheric? And is it pretty accurate, or is it just a new science project?
It's a great question. So we have different types of models that are out there that we're using. Because we're tracking individual particles and simulating kind of air particles moving backwards in time, and it is computation expensive, we typically want to keep our transport models closer to a region and a city versus a global transport model like geochem, which is what some atmospheric scientists use. And then EPA uses a different model called CMAC that actually incorporates the same transport mechanisms that I'm using in my model. So it's important for us to really understand if it's doing a good job of modeling that planetary boundary layer height, for example, as one of the things. So we test our models with measurements as much as possible, and we try to remove uncertainties as much as possible, but there's still some things that we don't get. So there's definitely room for improvement in understanding the complex kind of processes of just what the biosphere does. Understanding the emissions sources themselves, right? Methane is another big concern, another greenhouse gas, it's a big concern. And EPA, we have horrible data as far as like the pipelines and the oil and gas wells, and really understanding how many of them are there in Texas, for example, where they're located, how much they're leaking. So we actually still need improvement in collecting data of emissions inventories. We need improvements in being able to model some of these complex biosphere processes that remove and release CO2 into the atmosphere. And so we're getting there. But we incorporate as much as possible to get a better understanding of what we're seeing as far as background levels, as far as how much is being mixed up into the atmosphere. So it's as best as I can answer it without going into specific studies. So. Yeah.
How exactly does LiDAR specifically measure like carbon dioxide emissions? Because like you mentioned that LiDAR sends out photons. Like how does it know it's carbon dioxide and not sulfur?
Yeah, so actually what LiDAR is doing is not measuring carbon dioxide levels. What LiDAR is doing is measuring the layer that we breathe, the height of that layer and how it grows and decays throughout the day. So the measurement sites that we have in the Northeast use, it's called a Picarro system. And so those are actually measuring the CO2 levels. The LiDAR itself isn't doing that. The LiDAR is actually measuring the backscatter of the particles in the atmosphere. So when it hits a cloud or when it hits those aerosols, it's going to measure the light back, and so we can image the structures, but not necessarily CO2 itself. All right, well, thank you so much for joining me tonight, and feel free to ask me questions after. Thank you.